Bible Study, Episode 2, Continuation to What Science Is, by Keith Burgess. Introduction. In the last episode, we had a closer look at what Genesis chapters 1 and 2 had to say on the origins of life. We also had a short introduction to what science had to say. In this episode, we will be concentrating on what science has shown us on the origins of everything. What will be in this episode? The Big Bang Theory, the origins of the solar system, and the forming of the planets. The Big Bang Theory. The Big Bang Theory is a prevailing cosmological model on the early development of the universe. The key idea is that the universe is expanding. Consequently, the universe was denser and hotter in the past. Moreover, the Big Bang model suggests that at some moment all matter in the universe was contained in a single point, which is considered the beginning of the universe. Modern measurements placed this moment at approximately 13.8 billion years ago, which is thus considered the age of the universe. After the initial expansion, the universe grew significantly to allow the formation of subatomic particles including protons, neutrons, and electrons, though simple atomic nuclei formed within the first 3 minutes after the Big Bang. Thousands of years passed before the first electrically neutral atoms formed. The majority of the atoms that were produced by the Big Bang are hydrogen, along with helium and traces of lithium. Giant clouds of these primordial elements later coalesced through gravity to form stars and galaxies, and the heavier elements were synthesized either within stars or during supernova. The observable evidence for the Big Bang Theory. The earliest and most direct observational evidence for the fertility of the theory are the expansions of the universe according to Hubble's law, as indicated by the red shifts of galaxies. Discovery and measurement of the cosmic microwave background and relative abundance of light elements produced by the Big Bang necrosynthesis. More recent evidence includes observation of galaxy formation and evolution, and the distribution of large-scale cosmic structures. These are sometimes called the 4 pillars of the Big Bang Theory. Precise modern models of the Big Bang appeal to various exotic physical phenomena that have not been observed in terrestrial laboratory experiments or incorporated into the standard model of particle physics. One of these features, dark matter, is currently subjected to the most active laboratory investigations. Remaining issues include the Kuiper halo problem and the dwarf galaxy problem of cold dark matter. Dark energy is also an area of intense interest for scientists, but it is not clear whether direct detection of dark energy will be possible. Inflation and biogenesis remain more speculative features of current Big Bang models. Viable qualitative explanations for such phenomena are still being sought. There are currently unsolved problems in physics. The formation and evolution of the solar system. The formation of the solar system is estimated to have begun 4.6 billion years ago with the gravitational collapse of a small part of a giant molecular cloud. Most of the collapsing mass collected in the center, forming the Sun, while the rest flattened into a protoplanetary disk out of which the planets, moons, asteroids, and other small solar system bodies formed. The various planets are thought to have formed from the solar nebula. The disk-shaped cloud of gas and dust left over from the Sun's formation, the commonly accepted method by which the planets formed, is known as accretion, in which the planets began as dust grains in orbit around the central protostar. Through direct contact, these grains formed into clumps up to 200 meters in diameter, which in turn collided to form larger bodies, planetesimals, of 10 kilometers in size. These gradually increased through further collisions, growing at a rate of centimeters per year over the course of the next few million years. The inner solar system, the region of the solar system inside the 4AU, was too warm for volatile molecules like water and methane to condense, so the planetomeres that formed there could only form from compounds with high melting points such as metals like iron, nickel, and aluminium, and rocky silicates. These rocky bodies would become the terrestrial planets Mercury, Venus, Earth, and Mars. These compounds are quite rare in the universe, comprising only 0.6% of the mass of the nebula, so the terrestrial planets could not grow very large. The terrestrial embryos grew to about 0.05 Earth masses and ceased accumulating after about 100,000 years after the formation of the Sun. Subsequent collisions and mergers between these planet-sized bodies allowed terrestrial planets to grow to their present sizes. When the terrestrial planets were forming, they remained immersed in a disk of gas and cloud. The gas was partially supported by pressure and so did not orbit the Sun as rapidly as the planets. The resultant drag caused a transfer of angular momentum, and as a result the planets gradually migrated to new orbits. Models show that temperature variations in the disk govern this rate of migration, but the net trend was for the inner planets to migrate inwards as the disk dissipated, leaving the planets in their current orbits. The gas giants Jupiter, Saturn, Uranus, and Neptune formed further out beyond the frost line, the point between the orbits of Mars and Jupiter, where the material is cool enough for volatile icy compounds to remain solid. The ices that formed the Jovian planets were more abundant than the metals and silicates that formed the terrestrial planets, allowing for Jovian planets to grow massive enough to capture hydrogen and helium, the lightest and most abundant elements. Planetesimals beyond the frost line accumulated up to 4 Earth masses within about 3 million years. Today, the 4 gas giants comprise just under 99% of all the mass orbiting the Sun. Theorists believe it is no accident that Jupiter lies just beyond the frost line, because the frost line accumulated large amounts of water via evaporation from in falling icy material. It created a region of lower pressure that increased the speed of orbiting dust particles and halted their motion towards the Sun. In effect, the frost line acted as a barrier that caused material to accumulate rapidly at 5 AU from the Sun. This excess material coalesced to a large embryo of about 10 Earth masses, which then began to grow rapidly by swallowing hydrogen from the surrounding disk, reaching 150 Earth masses in only another 1,000 years and finally topping out at 318 Earth masses. Saturn may hold its substantial lower mass simply to have formed a few million years after Jupiter, when there was less gas available to consume. How we got our moon? At the end of the planetary formation in which the inner solar system was populated by 50 to 100 moons to Mars-sized planetary embryos. Their growth was possible only because these bodies collided and merged, which took less than 100 million years. These objects would have gravitationally interacted with one another, tugging at each other's orbits until they collided, growing larger until four terrestrial planets we know today took shape. One such giant collision is thought to have formed the Moon, while another removed the outer envelope of the young Mercury. Moons have come to exist around most planets and many other solar system bodies. These natural satellites originated by one of three possible mechanisms: co-formation from a circular planetary disk only in the case of the gas giants, formation from impact debris given a large enough impact at a shallow angle, and capture of a passing object. Jupiter and Saturn have several large moons such as Io, Europa, Ganymede, and Titan, which may have originated from disks around each giant planet, in much the same way that the planets form from the disk around the Sun. This origin is indicated by the large sizes of the moons and their proximity to the planet. These attributes are impossible to achieve via capture, while the gaseous nature of the gangways make formation from collision debris another impossibility. The outer moons of the gas giants tend to be small and have eccentric orbits with orbitary inclinations. These are the characteristics expected of captured bodies. Most such moons orbit in the direction opposite to the rotation of their primary. The largest irregular moon is Neptune's moon Triton, which is thought to be a captured Kuiper belt object. Moons of solid solar system bodies have been created by both collision and capture. Mars' two small moons, Deimos and Phobos, are thought to be captured asteroids. The Earth's moon is thought to have formed as a result of a single large oblique collision. The impacting object probably had a mass comparable to that of Mars, and the impact probably occurred near the end of the period of the giant impacts. The collision kicked into orbit some of the impactor's mantle, which then coalesced into the Moon. The impact was probably the last in a series of mergers that formed the Earth. It has been further hypothesized that the Mars-sized object may have formed at one of the stable Earth-Sun Hydronium points, either L4 or L5, and drifted from its position. The moons of trans-Neptunian objects Pluto, Charon, and Orpheus Fans may also have formed by means of a large collision. The Pluto, Charon, Orpheus Fans, and Earth moon systems are unusual in the solar system in that the satellite's mass is at least 1% that of the larger body. The Lagrangian points or Lagrangian points or L points or separation points are the 5 positions in an orbital configuration where a small object affected only by gravity can theoretically be part of a constant shape pattern with two larger objects, such as a satellite with respect to the Earth and Moon. Language points mark positions where the combined gravitational pull of the two large masses provides precisely the contrapuntal forces required to orbit with them. A satellite at L1 would have the same angular velocity of the Earth with respect to the Sun, and hence it would maintain the same position with respect to the Sun as seen from the Earth. Without the Earth's gravitational influence, a satellite of the Sun at the distance of L1 would have to move at a higher angular velocity than that of the Earth. Lagrangian points are the constant pattern solutions of the restricted three-body problem. For example, given two massive bodies in orbit around their common barycenter, there are 5 positions in space where a third body of comparatively negligible mass could be placed so as to retain its position relative to the two massive bodies. As seen in a rotation reference frame that matches the angular velocity of the two co-orbiting bodies, the gravitational fields of two massive bodies combined with the satellite's acceleration are in balance at the Lagrangian points, allowing the smaller third body to be relatively stationary with respect to the first two. When did water and life first appear on Earth? Water first appeared on Earth in liquid form around 4.3 billion years ago, and life appeared between 3.8 to 3.5 billion years ago. We evolved over this time from simple life forms to the complex life we have today through evolution, which I will do an entire series on.